16 miles until the service stopped. Miles and miles of black straight roads is enough.
Dan Olds here, and this is, boy, the fifth stop on my grand 2018 HPC tour. We are here at Sandia National Labs, and we've got the hardware honchos here. Please introduce yourselves.
Go ahead. I'm James Laros. I'm a computer architect. I'm involved in many of our programs to bring in advanced technology architectures and platforms into the DOE complex.
Okay, excellent.
I'm Ken Alvin. I'm Senior Manager for Extreme Scale Computing at Sandia.
And I'm Rob Hoekstra. I manage the Scalable Computing Architectures Department.
So, talking about extreme scale, I guess we're going to be talking about exascale pretty soon, right? That has to be on your roadmap.
It's certainly one of the things that we're involved in and trying to push technologies to mature and be effective in.
Okay.
And
okay.
we're looking beyond, conventional technologies for exascale into more non-conventional computing technologies going out into the future.
Okay. Let me hear from each of you, where do you think HPC and extreme computing is going? Or do we know?
I can tell you where I would like it to go.
That's good.
I'd like to see a manufacturing environment that accommodates more custom chips. So as we approach the end of Moore's Law and some very challenging manufacturing constraints in feature size, What I'd like to see is the space that is there on the dies, even currently, be used for more innovative approaches that might accommodate HPC even better. So rather than just putting more cores on a chip, I'd like to see more special purpose opportunities. So there's various ways we can do that, either partnering directly with a technology provider or in a more open sense, like the ARM ecosystem, for example, is a little more open. It might allow us to affect that a little bit easier.
Interesting. What do you think?
Well, so I agree with Jim. I think particularly in the next 5+ years, I think one of the things that we're hoping to help stimulate is, the creation of more system-on-chip technologies for high-performance computing, where you can put some more purpose-built circuitry that would replace some of the cores on a chip, that would be tuned particular to high performance with low power for our particular applications or our particular algorithms. And I think that there's strong precedent for this out in the mobile area, but it hasn't really taken hold in HPC. So one of the things we're hoping to do is to work with some of our sponsors, do some innovation in that area, and hopefully create a market or a set of conditions that makes that possible for us to do more customization in the future.
What do you think, Rob?
Yeah, so what I see happening is as device scaling opportunities have really disappeared, right? As we've kind of hit the end of Dennard scaling, we're seeing our community and the vendors start thinking more innovatively about architectures and how our performance on specialized architectures could be where we get the big win for our application performance. So I agree with what these guys have said. I think the likely path forward, and GPUs are a good example of, they are accelerators that accelerate certain classes of applications. We would like to see more and more examples of that for key mission applications. We'd like to see architectures become available that will dramatically accelerate the performance of our codes and give us and do that at probably at a much lower power and or hopefully cost as compared to our current machines.
Kind of sounds like you're making a case for FPGAs.
So FPGAs are a great example of what we would call reconfigurable computing, and certainly that's something that we're exploring today. FPGAs in and of themselves don't necessarily give you quite the level of price performance that you would like to get. I think going forward, we'll hopefully see more examples of reconfigurable computing that move us further in that direction. I think it's a great path to explore.
Yeah, I think FPGAs for us, can be a mechanism to achieve the end goal of some specialized on-die or on-package silicon. So getting an FPGA and integrating an FPGA tightly, having coherent FPGAs is a good vehicle for experimentation to understand exactly what it is that you want to optimize and how you could optimize it without having to go through the process of custom silicon. So it's really a nice vehicle from that aspect. Right now, the programming models, though, are really a stumbling block for us for FPGAs.
Yeah, that's certainly one thing. The programming models for FPGAs are not at all user-friendly for us. The other is that...
Well, they're using C and C++ in some of them now.
They're just starting to.
Just starting to.
And you really are
It's
not
still
you're really not exploiting the full power of the FPGA right now, or
Unless
anywhere
you're
close.
writing in one variable.
Unless you
Is
go
that
down
what it
to an
is?
RTL level.
OpenCL in the past was one mechanism, but that's just really not something that we do for our applications. So
We may get there.
Bar's too high.
And it sounds like ARM would be a very good vehicle for you guys to use in custom configuring it to your needs.
We could literally just do it ourselves,
Yeah.
as long as we were willing to, assume that cost. But it's quite a lot easier to partner with somebody when the basic ecosystem is open.
Mhm.
And, you know, we can basically just say, hey, you know, we've already done all this work, we would just like you to add this on package or on die in one of your next iterations, and there could be many ARM producers in the future versus a single producer of one technology or another. So it opens up a lot of possibilities.
Yeah.
And if you think about it, the ARM community has been very focused on mobile devices
Oh, yeah.
and heavy package level integration of specialized accelerators, different forms of acceleration, you know, video acceleration, things like this that you'd put in a cell phone, but they have a lot of experience in that space. So if we want to go in and say, hey, I want multiple chiplets in a package, an ARM provider is much more used to doing that type of manufacturing.
Mhm.
To your previous question, or this question, one of the things we're actually seeing some movement in that's a really good thing for us is memory technologies. So if you think back, the last time we actually had a bump in memory technologies is when the memory controller was brought into the die.
Yeah.
Back, AMD did
Long
that
time ago.
long time ago.
That's
So,
Opteron, early Opteron.
yeah, exactly.
Yeah.
So we're looking at a really long time, but now all of a sudden we're seeing the opportunity to have additional memory channels, HBM on package, other
That was
innovative
AMD
approaches.
Again, with 8 channels versus
Yeah.
6.
Well,
Yeah.
I don't know. So the first chip that came out that way, did AMD release one prior to our ARM chip? I'm not sure about
I
that.
think it was Epic. It's close.
Epic.
It's close. I think it was
Yeah.
Epic, though.
Epic
Yeah.
is, yeah.
Yeah, our current ARM chip has 8 channels per
Yeah.
socket. So
And that's a nice bump
it is
in memory bandwidth.
Yeah, it sure is.
But I just came from Los Alamos, and Gary Greider was decrying that memory bandwidth is just not accelerating
Right.
like anything else.
Right.
And
Yeah, so
Yeah.
towards a more balanced architecture is a very good thing for us. The one thing that, you know, I personally don't see improving that actually is a problem for some of our codes is latency. You kind of can't get around the speed of an electron, right? So how do we improve latency? You can't do it by improving the physical latency. So there's going to have to be methods of widening channels, you know, parallelism to just be able to kind of
hide the latency and other things.
yeah, we're going to have to take those sorts of approaches in the future. So
Interesting. What do you have here system-wise right now?
we are in the process of standing up Astra, which is an ARM-based supercomputer.
And that's I want to say is it the first ARM-based supercomputer of this size and scale?
Depends how you define. Well, certainly of this size and scale.
Right.
Okay. I mean, I know Mount Blanc is in Barcelona
Right.
Supercomputer Center. They've been working for a decade on ARM.
Well,
But they don't have anything this big.
No.
in the UK as well.
Yes.
But yes,
There's
we're,
Isambard in the UK as well, is another
Yes,
large system.
exactly.
So-
I forgot about
But
that.
ours is significantly larger than either of those.
Yeah.
So,
yeah.
And what's it come in at?
From
the-
How many
perspective, or
petaflops?
So its theoretical peak is 2.3.
Okay.
So far, we can say that we've exceeded a petaflop in our testing. You know, it'll be announced next Tuesday where we appear on the top 500 list for both HPL and HPCG.
Excellent.
We got some very good numbers for HPCG that are representing what we think about this architecture being a little bit more, or quite a bit more efficient for our types of applications.
Oh, really?
Yeah, so HPCG is a better representation of what we might see when we actually use our applications on a platform.
And HPCG is really much more representative of everything going on today, isn't it? As far as
Certainly in our
matrices.
field, yeah.
Yeah.
It's certainly much more representative of, you know, the kinds of engineering and physics applications,
Yeah.
types of solvers, types of algorithms we use.
Well, and I think Mike Carew, who developed HPCG with Jack Dungara and others, he tends to frame it as it's kind of at the limits or the bounds.
It's a bookmark.
Yeah,
Yeah.
high performance LIMPAC is compute bound, heavily compute
Yes.
bound, dense algorithms, while HPCG is much towards the other end of being memory bandwidth bound. So if you think about it, most of our applications, a lot of our applications are closer to being memory bound than
Yeah.
compute bound, but we run the spectrum depending on, so they give you kind of these bounds.
Yeah, and as Jack has said before, that HPL is about the best you're ever going to see out
Right.
of your system. HPCG is about the worst, and your real mileage will be somewhere in the middle.
Although I would say probably if you look at the average type of efficiency we get with our codes, it's probably much more similar to what the efficiency we see with HPCG than
Much closer
what
to
we
that
see with
side of
HPL.
the-
Yeah,
of
so
the bookshelf.
so I think most of our codes are kind of biased more towards the HPCG end of the benchmark results than the HPL. So.
Yeah, I think it's a really good step in the right direction to, for them to post HPCG scores and to try and make it into a thing. I know I'm trying to do it with the student cluster competitions and things because it's just much more real.
Yeah, we agree. Yeah.
So what's the future of you guys? What are you working on? What's going on? What breakthroughs can we expect to see that you can tell me?
Well, as far as, so if we continue on with Astra, which is the platform
Yeah.
we were just discussing, that's part of an advanced technology prototype program. So we hope to stay out ahead of technology and testing technologies prior to when we would want to use them on a more production system. So if we take an early technology like ARM, test it out, fill gaps in the software stack and the compilers. So compilers is a good example of ARM is ubiquitous, but it's never really been used for high performance computing.
No.
Therefore, the vectorizing compilers, things like that are behind at the moment. So it's kind of like this perfect storm for our first platform in the Vanguard program. But going forward, we hope to do the same thing repeatedly. So, and this applies to both technologies and to vendor partners. So we've seen a kind of a contraction in the number of integrators that were basically trained or basically capable of proposing on some of, especially our largest platforms. And that's not a good position for the NNSA to be in. You know, we want a lot of bids and a lot of choices for our next system. So not only are we going to try to, test out these new technologies and fill the gaps and harden them, improve the viability for our mission codes, but we also want to work with new vendor partners whenever possible and get them used to what it's like to deliver a platform to the DOE and for our unique, fairly niche purposes. And so far, that's going really well.
Okay, so you're reaching out to them. Go ahead.
Yeah, so our prototypes program is really intended to buy down this risk that the labs and our federal program, we want to stay out in the forefront of the technology that's coming along, but we also need to deliver to our mission.
Of course.
And so that tension has always been in the work that we do in high performance computing. And so our intent with the prototypes program is to be more intentional of bridging the gap between the early technologies that we can explore through small test beds and the kind of large scale, large investment platforms that we do. And so with a more modest investment, we can really close some of the gap in terms of the risks that we encounter. And it could be the development tool chain, system administration and tools, lots of things through the software stack, as well as satisfying ourselves that the technology is the hardware technology is mature enough, and then that we can get an opportunity to test our codes out at scale. Maybe not at the most extreme scale that you would see with an exascale machine, but sufficient scale that it's sensitive to the to the readiness of the interconnect network, what's happening on node, and so forth. And so, that's what we're doing with Astra and with our prototypes program, and our intent is to move forward along those lines. And that's one of the great values we can give back to the broader community is to try to, bring some of these technologies to production and to having impact much sooner as a consequence of doing this.
And to kind of foster those new technologies.
Right, and provide some ability to bring the companies that are beginning these investments, to provide them with some opportunities to begin to move them forward in the marketplace.
That's a very important role.
Yeah.
Yeah, and to reiterate, I mean, we've had a lot of success with our advanced architectures testbeds program, which is a much smaller scale, from a few nodes to maybe a rack scale. And this prototype effort, these moderate scale systems are an attempt to then bridge that gap and say, oh, okay, we've explored this very advanced pre-release technology with a vendor. Now we want to make it viable for a $100+ million procurement by DOE or one of the other agencies in reality. And the test beds have been a great stepping stone towards that. It's given us a place to work with the vendors and explore these early technologies, and played a big role in our decisions for the Vanguard program. You know, we had very early ARM-based hardware for years prior to making the decision to pursue it as a part of the larger Vanguard Astra system. So.
Interesting.
Yeah, you could make a direct tie with our FPGA example. So we would probably first attack an FPGA in the testbed program with a few nodes and really kind of work things out. But as we matured that and made decisions,
because that's where we see the opportunity to get the greatest leverage and the greatest impact, is if we partner closely with that much larger community. So.
Very much part of the mission.
And I guess the other comment I'd make is, you know, we didn't talk that much about software, but I think that's an often neglected
Software, who cares?
You know,
No, you're right.
The complexity, diversity, and disruptiveness of all of the new computing technologies that, you know, are coming along that have potential use for HPC. Really, I think we look a lot toward, you know, system software and software stack advances to try to make those things really viable for us, you know.
Sure.
Because oftentimes the way these things are initially delivered or, you know, made available to us are just like the FPGA example that we gave earlier. You know, they're not at all user friendly, and if we don't work the system software pretty much in tandem with investing and, you know, working with vendors on hardware, then, you know, we're really not tapping into the potential of these new technologies at all.
They all have to have an ecosystem.
And all of these things are extremely disruptive to our end user application code. So we've got to build, you know, that trail or tiers of the software stack that make those things really viable to be used by somebody writing a physics code. So.
Yes, absolutely. And you're not going to have successful hardware unless there's an ecosystem for it.
Exactly. Yeah. Yeah. And so, you know, with Astra, that's been, you know, really a strong focus of the work that's going on, working with the other laboratories. It's not just about putting the hardware on the floor, but it's also working pretty large software environment effort.
I would imagine.
Yeah, with one of the big goals being shrinking that time between when the platform hits the floor and when it actually really starts showing significant value to mission workloads.
Right.
Yeah.
Right.
Yeah.
Yeah, there's so many aspects of that. I mean, some of it the laboratories can address, which we're doing with our ATSE program. It's an Advanced Technology Software Environment Program. And we expect that to live beyond the ARM architecture, but right now we're addressing the gaps in ARM. But gaps that the laboratories can address, like compilers and optimizations of libraries, we partner with companies like Cavium for microarchitecture optimizations, ARM itself for the compilers, to try to have them focus more on things that are important to us that may be second or third on their list unless we partner with them to accelerate those efforts. So we can really kind of attack, you know, under Vanguard, we can kind of attack every dimension of the problem because we have the ability to do it either within the lab or by partnering with other companies.
And there's going to be some interesting ARM developments. I was with the at the HPC Advisory Council event, and EPI, the European Processor Initiative, folks were presenting, and they're going to be pushing hard on getting ARM for exascale.
Well, and there's of course the next Riken system, the post-K system coming up soon as well. So,
Yes.
and they've already announced their ARM-based architecture for that
Yes.
system. So.
So interesting things afoot. A lot more diversity and heterogeneity in your hardware choices. That's why we have
Yep.
brave men like you going through those hardware choices, putting them in a test bed, figuring out what's viable, what's not viable. It's a work that has to be done.
Yep. Brave, crazy.
I feel like this is a big
It's a blurred line.
point to drop the mic.
Well, on that note, thank you for taking the time to talk to me and participate in the grand 2018 HPC Road Trip. And we will see you in Dallas.
All right,
Okay,
thanks.
Thanks, Dan.
I got